Next, we are going to talk about how to do classification. Here we only talk about a shorter version. Because the time is limited, let's talk about a version that can be finished in 20 minutes. There is a longer version. If you want to see the longer version, you can take a look at the video of previous years. It is 2 hours, or maybe 3 hours for the longer version. For classification, I will tell you how to do classification as short as possible. How to do the classification? We have already talked about it. Regression means you use a vector as the input, and then get the output value. We want the output value and a certain label, which is what we want to learn, to be as close as possible. Some students may ask, why is there a hat symbol in the target label, but not in the predicted label? You may have seen it elsewhere that there is a hat in the predicted label. There are no certain rules for the notation. If you take my machine learning class first, you may ask other teachers why there is a hat in the predicted label and no hat in the target label. In this course, if it is the correct answer, add a hat. If it is the output of the model, don't add it. There is a possibility that, if you can use regression, we can treat classification as a regression. How to say that? Although the method is not a good method, it is a tricky method, you can still use it. After using a vector as the input, our output is still a scalar. And it's y. We want to make y and the correct answer as close as possible. But, y is a number. How can we make it as close to the class as possible? We must also transform the class into a number. For example, class 1 is number 1. Class 2 is number 2. And class 3 is number 3. What we are going to do next is, we hope that y can be as close to the class number as possible. But, would it be a good solution? If you think about it thoroughly, under certain conditions, it may be imperfect. Because, if you assume that class 1 is number 1, class 2 is number 2, and class 3 is number 3, it means that you consider class 1 and class 2 are closer than class 1 and class 3. The class representation, like this, sometimes works, but sometimes it doesn't. Supposing, among class 1, 2 and 3, there are some kinds of relations. For example, based on a person's height and weight. You want to predict what grade a primary school student is. First grade, second grade, or third grade? In this situation, the first grade may actually be closer to the second grade. And the first grade may actually be further to the third grade. But, supposing, among these three classes, there is no specific relation. Assigning that class 1 as 1, and class 2 as 2, and class 3 as 3, is weird, because you hypothesize that 1 and 2 have a relatively close relation, and 1 and 3 have a relatively far relation. So, what should we do? When you are doing classification tasks, a common approach is to represent your class as an one-hot vector. For the one-hot vector, we saw it in homework 1, right? In homework 1, I mentioned that we transformed the states of the United States into one-hot vectors. For the same reason, we can use one-hot vectors to represent different classes. If there are 3 classes, our label, y hat, is a 3-dimensional vector. If it's class 1, it's 1 0 0. If it's class 2, it is 0 1 0. And if it's class 3, it is 0 0 1. You use a one-hot vector to represent a class. And if you do so, we won't say that class 1 and class 2 are closer, and class 1 and class 3 are further. If you use one-hot vectors to calculate the distances between any two classes are the same. Okay, what's next? If our goal, y hat, is a vector, y hat is a vector with 3 elements, then our network should also output 3 numbers. The networks we've mentioned before are only output 1 value, because what we did in the past are regression problems. Networks only output a number. How to make it output 3 values? Actually, it is the same. As long as you can output 1 value, you can output 3 values. Repeat the operation 3 times. You multiply a1, a2, a3 by 3 different weights and plus bias. You can get y1. Multiply a1 a2 a3 by other 3 weights. And add another bias to get y2. Then, multiply a1 a2 a3 by another set of weights. And add another bias to get y3. In this way, you can generate 3 numbers. So you can input a feature vector. Produce y1 y2 y3. And expect that y1 y2 y3 are close to our goal. Okay, so now we know how regression works. We input x and make the output and the label as close as possible. What if it is classification? We just said that input x may be multiplied by aw plus b, and be sent into an activation function. Then we multiply by w prime and add b prime to get y. Note that our current y is not a number, but a vector. So, when doing classification, we will often pass y to a function called Softmax first to get y prime. Then we calculate the distance between y prime and y hat. In other words, we have to make y prime and y hat as close as possible. Why do we use Softmax? There's a relatively simple explanation. I actually thought about it for a long time. How can I finish this part in 10 minutes? In the past lectures, I took a long time to tell you why Softmax is used here and what the assumptions behind it are. We would start with the generative model first. Then we went all the way to logistic regression to let everyone know why we put a Softmax here and what the historical background it has. We are not following that path anymore, so it suddenly becomes difficult to explain why we put a Softmax here. Here is a quick explanation to get this over with. The value in y hat contains both 0 and 1, right? It is a one-hot vector. Therefore, the values inside are only 0 and 1. How about y? It can have any value. Our goal is only 0 and 1. But y can have any value. Can we normalize this value first? Move them to the interval between 0 and 1. This way, it is easier to calculate the similarity with the label. This is a relatively simple way of explanation. If you really want to know the reason we use Softmax, you can refer to previous lesson videos. If you don't want to know, you just remember one thing. Things that this Softmax does is to change any value in y to some value between 0 and 1. How does Softmax work? This is the block of this Softmax. Enter y1 y2 y3. It will produce y1 prime y2 prime y3 prime. The operation inside is like this. We first take all y with an exponential. So no matter if y is positive or negative, after taking exponential, it's all positive, right? Even if it's a negative number, a value less than 0. It also becomes positive after taking exponential. Then you normalize it. Divide the sum of all exponential values of y. Then you get y prime. The graphical explanation looks like this. y1 takes exponential, y2 takes exponential, y3 takes exponential. Sum them up. We get a summation. Place the summation in the denominator. Next, divide exponential y1 by the summation. Divide exponential y2 by the summation. Divide exponential y3 by the summation. We get y1 prime y2 prime y3 prime, and that's it. With this formula, you will find out that this y1 prime, this yi prime y1 prime y2 prime y3 prime, they are all between 0 and 1. For this y1 prime y2 prime y3 prime, their sum will be 1. We can give an example. Originally, y1 equals 3, y2 equals 1, and y3 equals -3. When we take the exponential of these numbers, we have the following. E to the power of 3 is 20. E to the power of 1 is 2.7. And e to the power of -3 is 0.05. After normalization is done, we have 0.88, 0.12, and 0. So, this is what the Softmax function is used for. In addition to normalization, which makes all the y primes stay in the range of 0 and 1 and sum up to 1. It also has an added bonus. It makes the gap between large values and small values even larger. So, originally we have the value of e to the power of -3. That value approaches 0 after it's normalized. The inputs of the softmax function are often called the logits. For the sake of convenience, we gave it a name called logit. In this particular case, there are 3 classes. What if there are only 2 classes? If there are only 2 classes, it is still totally fine to use the softmax function. But, perhaps the method you hear more often is, instead of using the softmax function, we use the sigmoid function when there are only 2 classes. So, when there are only 2 classes, what is the difference between using the softmax function and using the sigmoid function? You can try to figure it out yourself. If you think about it, these 2 methods are actually equivalent. I know that because we showed the softmax function on the slides. It implies that the softmax function should also work just fine with 2 classes. There's no doubt about it. However, when there are only 2 classes, it is more common to use the sigmoid function. You might wonder what the differences are between these 2, and which one is better. Let me tell you that they are exactly the same. You can calculate the derivation by yourself, and you will find that these 2 things are the same. So after we input x to a network and generate y, we will get y prime through softmax. Then we calculate the distance between y prime and y hat. This distance is denoted by e. There is more than one way to calculate the distance between y prime and y hat. For example, if I want this distance to be the mean square error, which is exactly the same distance as we use the homework one, we take every element of y prime out, and also take every element of y hat out. Then we calculate the square of their element y's difference and sum them up as the error. This is a practical way to calculate the distance between 2 vectors. In other words, by minimizing the mean square error, we can make y hat equal to y prime in the end. But there is another more practical and more common way, which is called cross-entropy. The formula may seem weird at first glance. What does this cross-entropy mean? Let's take a look now. What does this cross-entropy formula look like? It is a summation over all I. Then, we take out the ith element of y hat and multiply them by the natural log of the ith element of y prime and sum them up. This is called the cross-entropy. When y hat is exactly the same as y prime, you can minimize the value of cross-entropy. When y hat is exactly the same as y prime, the value of mean square error will also be the smallest. And the error of cross-entropy will also be the smallest, too. But why do we have such an odd formula called cross-entropy? To make the long story short, we can say that minimizing cross-entropy is actually equivalent to maximizing likelihood. You may have heard the word likelihood in many places. So in this class, we remove the word likelihood. We now don't have the word likelihood. So we can't explain it in this way. We can't say why minimizing the cross-entropy is equivalent to maximizing the likelihood. We no longer know what likelihood is. But these 2 things are actually equivalent. So suppose someone asks you one day, if we are doing a classification problem today, what's the relationship between maximizing likelihood and minimizing cross-entropy? Please don't answer that they are actually very similar, but with a very subtle difference. It's not like this. They are exactly the same thing. It's just a different way of saying the same thing. When we are training a classifier, if maximizing the likelihood is acceptable, minimizing the cross-entropy should also be acceptable. But we didn't talk about it. How can I convince you that we should use cross-entropy? The next slide tells you that cross-entropy, from the perspective of optimization, is more suitable for classification than mean square error. Cross-entropy is more commonly used in classification than mean square error. How commonly it is used? It is so commonly used in PyTorch that cross-entropy and softmax are tied together. They are a set. As long as you call the cross-entropy function, Softmax is automatically included in the function. So if you look closer at the program for TA's assignment 2, you will not find any Softmax function. Originally, Softmax should be part of the network. When you define the network, you should also define the Softmax function. But you find that in the TA's sample code, you can't find any Softmax. Why? Because it is integrated in the cross-entropy function. When you use cross-entropy in PyTorch, PyTorch will automatically help you add Softmax to the last layer of your network. So if you are using PyTorch today, when you add Softmax to the network and use cross-entropy at the same time, it will do the Softmax function twice. This design is interesting in PyTorch. So this fact shows that Softmax is often combined with cross-entropy. They are a set and will usually be used together. Next, I will tell you why cross-entropy is more commonly used in classification compared to mean square error from the perspective of optimization. For that part, you can prove it by mathematics. But in my slides, I will explain this with examples. If you want to see the mathematical proof, I put the link here. You can watch the video from previous years. If you don't want to know, then we will give you an example to show you why cross-entropy is better. Okay, suppose we have to do a 3 classes classification. And my network first outputs y1, y2, and y3. After passing Softmax, it will output y1 prime, y2 prime, and y3 prime. Let's assume that our correct answer is 100. We are going to calculate the distance between the vector of 100 and y1 prime, y2 prime, y3 prime. Then we use E to denote this distance. E can be mean square error and also cross-entropy. Okay, let's take a look at the E, which is set to mean squared error. What is the difference in the error surface compared to the cross-entropy? Assume that y1 changes from -10 to 10. And y2 also changes from -10 to 10. y3 is set to -1000. Because y3 is very small. After taking Softmax, y3 prime is very close to 0. It is very close to the correct answer. And it has little influence on our results. In short, we set a fixed value for y3, and only observe when y1 and y2 change. The loss is calculated by adding up a lot of E. What kind of influence does it have on our loss? These 2 pictures below are the loss corresponding to the change of y1 and y2, or the impact on the error surface, when E is set to mean squared error and cross-entropy respectively. If y1 is large and y2 is small, then y1 prime will be very close to 1. y2 prime will be very close to 0. When y1 is large and y2 is small, the loss is small. For both mean square error and cross-entropy, color red here represents a large loss, and color blue represents a small loss. In the upper left corner, y1 is small and y2 is large. If y1 is small and y2 is large, then y1 prime is 0 and y2 prime is 1. The loss is larger in this situation. The loss is large in the upper left corner, and small in the lower right corner in both pictures. So we expected that, when the training ends, the parameters should go to the lower right corner. But, what if we start from the upper left corner? If we choose cross-entropy as the loss function, the slope is non-zero at the upper left corner. So it is possible for you to follow the gradient vector and reach the lower right corner. However, if you choose mean square error, you're stuck. Mean square error's shape is very flat at places where the loss is large. In other words, at those places, its gradient is very small. If you started there, you are far away from your goal, since the magnitude of the gradient is too small. And you will have a hard time going to the lower right corner by gradient descent. So if you choose mean square error as the loss function, you are very likely to fail in training a classification model. But if you have a good optimizer, it is a different story. If you are using Atom, whenever you are at places where the gradient is too small, The optimizer itself automatically increases the learning rate for you. Maybe you still have a chance to reach the bottom right corner. But still, this choice of loss function may make your model harder to train. This is a good example, in which tells us the choice of the loss function may affect the difficulty of training. I had told you about using the Shenluo Tianzheng to smooth the error surface. Here we have a good example that changing the loss function surprisingly affects the difficulty of optimization.